Assalamu alaikum. This is lecture number 8 of the Control Systems course. In the last lecture, we studied the mathematical modeling of electrical networks. And in this lecture and the next lecture, we will study the mathematical modeling of mechanical systems. So firstly, we will see only the translation mechanical system, which only moves in the horizontal direction and they do not rotate. So just like the electrical networks, we have three components here in the mechanical networks. The first one is the spring, second one is the viscous temper, and the third one is the mass. And these three components are actually analogous to their electrical counterpart. So two of them are the energy storage elements, the spring and the mass, or the energy storage elements, just like the inductor and capacitor in the electrical networks. And the viscous temper is the energy dissipative element, just like the resistor in the electrical networks. The force velocity, the force displacement, and the impedance relationship are shown here, where the K is the spring constant, where Fv is the coefficient of viscous friction. We will model the mechanical system by using the Newton's law of balanced forces, which states that the sum of forces on a body equals 0. The analogies of electrical and mechanical networks can be studied in detail by comparing the tables. If we compare the voltage-current relationship in the electrical circuits with the force-velocity relationship in the mechanical components, we can see from here that the mechanical force is equivalent to the voltage in electrical networks, and the velocity in the mechanical networks is equal to the current in the electrical networks. And also from the force displacement column and the voltage charge relationship, we can see that the charge in the electrical network is equivalent to the displacement in the mechanical network. So to model the mechanical systems, we will employ the following steps. So firstly, we will find the differential equation of the mechanical system, which is normally called the equation of motion, or generally written as EOM, equation of motion. And to find the equation of motion, firstly we will assume a positive direction of motion, for example to the right, and it is generally expressed as this symbol. This shows that here's some body, and the default direction of the displacement of the body is towards the right, and generally we represent a body by its mass. The second step is to draw a free body diagram, and in the free body diagram we place all of the forces that act on the body either in the direction of motion or opposite to it on the body. And after that, we use the Newton's law to form a differential equation. So after we have found a differential equation, we take the Laplace transform of the differential equation, and from there we find the transfer function of the system. So let's find the transfer function of a simple mass spring damper system shown here, with the mass m and the spring coefficient k and the viscous friction Fv. So the first step in the modeling of a mechanical system is to find the differential equation or the equations of motion, and we have just studied in the previous slide that to find the equation of motion, firstly we have to draw the free body diagram. So in the free body diagram here, we can see that we have a mass m. This represents the body itself and all of the forces applied on the body. The forces which are which move the body in the direction of the motion x of t are shown with the right arrow, like the applied force, and all of the other forces which moves the body away from the positive direction are represented with the arrow to the opposite direction, like these three forces, which represents the forces due to the spring, due to the mass, and due to the viscous friction. So after this, we will apply the Newton's law to find the differential equation. And then Newton's law states that sum of all the forces will be equal to 0. So here we have added all the forces. This is the force due to the mass itself. This is the force due to the damper. And this is the force due to the spring. And finally, this is the force which was applied on the body. From here we can see that we can represent this force by a negative sign on the other side and equate this whole equation to 0, or we can move the applied force on the right side, and now we can represent this whole equation equal to f of t. So after this, we have applied the Laplace transform and we find this equation. From here we can take the x of x common, and as we were asked to find the transfer function between x of s and f of s, so x of s is the output of the system and f of s is the input of the system. So from here we can find the x of s divided by f of s, which is the transfer function of the system, and this is your final transfer function. There's also another easier way to find the transfer function of mechanical systems. Firstly, we transform this free body diagram into its equivalent Laplace transformed network or Laplace transformed free body diagram, where we transform each component into its equivalent Laplace transformed impedance. And from here we can directly write this equation. We don't have to find a differential equation by this way, and after that we can easily find the transfer function. So if we have a free body diagram in the Laplace transformed orientation, we can directly find this equation of motion by using this observation based method, which states that sum of all the impedances multiplied with the x of s will be equal to sum of all the applied forces. And we can see that it is done here, that all the impedances are added together and multiplied with x of s, and this is kept equal to f of s, which was the applied force. So by this way we can convert any mechanical system into the transfer function directly. We can also find the transfer function for translational mechanical systems with more than one bodies or more than one moving points. So the required number of equations of motion will be now equal to the number of linearly independent motions. What does the linearly independent motion means? It means that a point of motion in a system can still move if all other points of motion are held still. So let's suppose we have two bodies here, one with the mass m1 and another with the mass m2, and both are connected with this spring with the spring coefficient k. So from here we can see that both of the bodies can be moved irrespective of the other one. So if I hold m1 still, this one still, I can still move the m2, and similarly if I hold m2 still, I can still move the m1. So this is an example with a system with two linearly independent motions. So to model this particular system, we will require two equations of motion, one for m1 and the second for m2. We have another name for number of linearly independent motions, which is degree of freedom, and generally it is written as DOF. So now let's find the transfer function of the following system. So if we observe this system, we can see that we have two bodies, one with the mass m1 and one with the mass m2. m1 is connected to the wall by a spring with the spring coefficient k1, and similarly m2 is connected to another wall by a spring with the spring coefficient k3. And both of these masses are connected to each other by another spring with the spring coefficient k2, and also another damper with the viscous friction Fv3. And also in this example, we consider the friction between the mass and the ground. And the friction between mass m1 and the ground is modeled as the viscous friction Fv1. And similarly, the friction between the ground and the mass m2 is represented by, again, the viscous friction Fv2. So from here we can see that now we have two displacements here. One is the x1 and the second one is the x2. And the direction for both of these displacements is taken as positive, that is to the right. And we can also see that we have one applied force here, which is F of t. So to model this example, firstly we will have to draw the free body diagram for each point of motion, and after that we will use this superposition to combine all of the forces together. So to draw each free body diagram for a mass, firstly we hold all other points of motion still and find the forces acting on the body only to its own motion. And then we hold the body still and activate all other points of motion one at a time. In this case, we have only 2 points of motion. We will hold one body still and activate the other body and see its effect on the current body. For example, so firstly, I want to find the free body diagram for M1. So what I will do, I will hold M2 still and move M1, and we can see that M1 can be moved in this direction as well as in the other direction. Now I will note down all of the forces acting on M1. After this, I will hold M1 still and move M2, which again can be moved in this direction as well as in this direction. But we will only note those forces which act on the M1. And similarly, we will repeat the process for M2 as well. As in this example, we have 2 points of motions. So it means that we will have 2 degrees of freedom. And we know that the degree of freedom will be equal to how many simultaneous equations we will get. So in this case, we have 2 degrees of freedoms. So we will get 2 simultaneous equations of motion. The first simultaneous equation of motion will be for the mass m1 and the second simultaneous equation of motion will be for the mass m2. So let's find the equation of motion for the mass m1. We have already discussed that for the equation of motion for m1, we will firstly draw the free body diagram for the mass m1, and firstly we will consider only those forces which act on m1 due only to the motion of m1. So it means that we held m2 still, and now we want to find out that how many forces are acting on the m1 when we move only m1. So we can see that one is the force due to the applied force, the other is due to this spring, the other is due to this friction, the other is due to the mass itself, and there are two other forces. One is due to this viscous friction, and the other is due to this spring. So how many total forces are there? There are 1, 2, 3, 4, 5, 6 forces being applied on the mass m1, and we can see in this figure A that we have total 6 forces. Now we want to find the directions. So we can see from here that if we move m1 in the positive direction, that is to the right, we can see that all of the other forces are against the x1 direction, and the only force is the F, which is towards the direction of x1. Hence you can see that all of the arrows are on towards the left side. Only the force has the arrow to the right side. So in the next step, we will hold the m1 and we will move the m2 and see the effect of m2 on the m1. We will only note down those forces which have the impact from m2 towards the m1. So if we move m2, so we can see that the forces due to FV3 and K2 has an impact on m1. That's why we have noted down these two forces here. And after that, when we have noted down all of the forces acting on the m1 due to the m1 itself and due to the motion of m2, we will now combine all of these forces, and all of these forces in the figure A and figure B are now combined into the figure C. Now we will find the free body diagram for the mass m2. Again, we will follow the same procedure. Firstly, we will find all of the forces on m2 due only to the motion of m2. So we will hold the m1 mass still, and we will see how many forces are acting on the m2. So from here we can see that one is the force due to this K3, one is the force due to this friction, one is the force due to this friction, and another force is due to the mass, and one is the force due to the mass itself. So we have 1, 2, 3, 4, 5 forces, and all of these forces are acting against this displacement x2. So that's why we can see that in this free body diagram here, all of the forces are all of the forces have the arrow in the opposite direction of x2. So now let's hold the m2 mass still and move the m1 mass, and we can see that the effect of m1 is through this and this friction and this spring. And we can see that if we move this mass in the positive direction, and that is in the direction of x1, it will have a positive impact on the direction of m2. It will encourage the mass m2 to move towards the direction of displacement x2. So that's why we can see that the arrow on these two forces is towards the right side. In the figure C, we will combine all of these forces in the figure A and figure B, and after this superposition, we have the final free body diagram for the mass m2. Once we have found the free body diagrams for the mass m1 and the mass m2, the next step is to find the equations of motion. So we can find the equations of motion by directly observation-based method. So for the first mass and the first free body diagram, we will have the first equation of motion, and this equation of motion can be directly found by the observation-based method. We will just add the corresponding impedances for x1 and x2, and in the case of mass 1, the corresponding displacement x1 will be with a positive sign and the other displacement will be with a negative sign. Similarly, for the next mass having this free body diagram, we will have the second equations of motion. In this equation of motion, we will add all of the impedances for the case of x1 and also for the case of x2, and the sign with the x2 will be positive and the sign with the x1 terms will be negative. After we have found the equations of motion written here, the next step is to find the actual transfer function. In this case, we were required to find the transfer function x2 of s divided by f of s. So the above system of simultaneous equations can be solved by using the Cramer's rule. So if we want to find the transfer function x2 by f, we firstly have to find the x2 from these simultaneous equations. And to find the x2, we will apply the Cramer's rule. And if we apply the Cramer's rule on this system of simultaneous equations, this will be x2 of s, which will be equal to, so we will have firstly this term, which I represent by, let's suppose, a here, and then this term, which I represent by, let's suppose, b, that will be here. And then on the next column, we will have this column as it is, f of s and 0, divided by the delta, and the delta is represented here. So from here, we can see that if we multiply a with the 0, it will vanish, and we will have minus b into f of s divided by this delta. Now we can put the value of the b here, which is negative, and negative signs are cancelled out, and we will have just fv3s plus k2 multiplied with the f and divided by this delta. So now we have x2 equals to this whole term, but what do we need? We need x2 by f. So we can cross multiply f over there, and we will have x2 of s divided by f of s, which will be equal to this whole term divided by this delta. And this transfer function is, by the way, written over here. So this is your final transfer function of the example we just studied. And this delta can be solved by finding the determinant here, written here. In the previous slides, we studied a systematic way of finding the equations of motion for a given mechanical system. We can also find the equations of motion directly by observation. We will take the previous system again here, where we had two bodies with the masses m1 and m2. And the motion of m1 is represented by the displacement x1, and the motion of m2 is represented by the motion x2, or the displacement x2. Now we can find the equations of motion by using this observation-based method. So for the first equations of motion for the mass m1, we can add all of the impedances connected to the motion at x1 and multiply it with the x1 here, and then we will add all of the impedances between x1 and x2 and multiply it with the x2, and all of these terms will appear with a negative sign, and on the other side is the sum of all the applied forces at x1. We can verify this method by looking at this equation of motion, where these are sum of all the impedances which are connected to the motion at x1, which are connected to this motion. And similarly, these are all the impedances which are connected between m1 and m2, and this is the only force which is applied on the mass m1. And similarly, we can find the equation of motion for the next mass. Although it is tempting to use this method to find the equations of motion, as this is a very simple method, but it requires a lot of experience to correctly model the equations of motion directly. So it's a better idea to first solve the systems by the systematic way studied earlier, and then when you have a greater understanding of the modeling, you can directly model the system by the observation-based methods discussed here.